Transistor. Transistor, it's like very important device, and it has lot of application, and from exam point of view also it's very important. And just now we saw diode. Diode basically when two, you can say one N and one P type semiconductors are clubbed together, and then they are forming a diode. Transistor is little bit different. Simple terms, here actually three semiconductors are there, 2N and 2N, like that can be like two-way, either 2N 1P or 1N and 2P. So based on like how they are, they can be categorized in two categories, either NPN or PNP. In another way I can say a transistor is a device where between two N-type semiconductor, one P-type semiconductor is switched, or between two P-type semiconductor, one N-type semiconductor is sandwiched. Sorry, not switched, it's sandwiched. Is it? So here transistor, it has actually three semiconductor, and here either between two P-type semiconductor, one N-type semiconductor is sandwiched, or between two N-type semiconductor, one P-type semiconductor is sandwiched. So let's consider these are here three semiconductors. Try to focus here everything. It's like thickness and all, every detail is important here. So normally this is one semiconductor, another semiconductor, and this is, and normally we have actually like two terminals in any device, but here in case of transistor there are three terminals actually. And another thing is we call this as emitter. One semiconductor is termed as emitter, the middle one is always termed as base, and this one is termed as collector. So another terminal is called as collector. These are name of three semiconductors in a transistor. So it doesn't matter whether this is NPN or PNP. These one will be always emitter, another will be base, and the last one will be collector. They have something like special properties about these, why, which one will be emitter, which one will be base, and what will be like the properties of collector. So one thing is we can talk about in terms of thickness, and another parameter is doping. N-type, if it is N-type, then definitely pentavalent doping, and if it is P-type, it will be trivalent doping. So in emitter, it's, you can say it's highly doped, or you can say among all these three, it's having maximum doping, so highly doped. Is it? Base, you can say it's lightly doped, and collector, it's moderately. Thickness, if I talk about, it's like moderate or medium size. This is the thin or thinnest among all three, and this is the largest or thick. So this is the like how about the construction. So definitely emitter junction doping is highly doped, and thickness is medium. Base, it's like thin among all these three and lightly doped, and collector, it's basically thick and moderately doped. So this is about, so basically there are three parts: emitter, base, collector. This is there about thickness, and this is the like how they are related about doping. So now see here, this is emitter, which is highly doped, and depending on like if it is NPN, both these two are N, this can be P, or it can be P, and middle one is N. In case of NPN, here you can say the emitter is having majority charge carrier, that is electron. In case of PNP, emitter, in all cases like whether it's PNP transistor, NPN transistor, emitter is like highly doped, so it is the supplier of charge carrier. In transistor, it's basically current driven. Here it work based on current. Actually it supply a transistor. Here it means transfer of resistance, but here there is no filament, no heating, nothing is there, still it can transfer resistance. So we will try to understand exactly like how it is and how it actually work and how we can use transistor in different possible ways. So mainly we will discuss about three ways, that is how transistor can be used as amplifier, transistor as a switch, and transistor as a oscillator or feedback oscillator. So first thing is, this is about its construction. So there can be like two type of transistor. One is NPN transistor. So in this case you can say between two N-type semiconductor, one P-type semiconductor is sandwiched, right? So this is NPN, three terminals, and based on thickness also you can identify this will be emitter, base, and this will be collector. So here doping will be like highest. Here you can say number of charge carrier, it's like will be maximum. This is your emitter. Holes, here it will be like lightly doped, so it will have like few excess charge carrier holes, and it will be like again collector, but it's moderately doped. So this is the situation. Now see here, it's highly doped, and between two like N and P diodes or two semiconductor, there will be one junction and it's highly doped. So you can definitely see here the thickness, what will be the thickness of depletion layer here for case of emitter and base. So the thickness here will be moderate, or you can say if I compare with this one, then it here the doping is less, so thickness will be high. So this will be the situation here. And now what happened, like depletion layer will be just a normal between, like you can, when you are talking about base and collector, you can just forget about this, pass this side. When you're talking about emitter and base, you can just forget about this part. So now in this situation, like here what is happening, it's p type, holes concentration will be higher, they will diffuse this side, electron will diffuse this side. So you can see here negative will appear, negative charge will appear on this side, and some positive charge will appear on this side. So this is some potential barrier. Similarly here some negative charge will appear this side and some positive charge will appear on this side. So this is about a depletion layer. Here it will be like comparatively thin as doping is higher, and this is comparatively thick. Clear? This is your NPN transistor. In this situation, when it is like connected to some circuit, always here this is emitter, base, collector. So in operation, in working, basically this can be connected in many different possible ways. It can be forward bias, it can be reversed bias, both can be forward bias, both can be reversed bias, this can be reversed bias, and this can be forward biased, is it? So first thing is always like emitter will supply electrons, because majority charge carrier, here you can write majority charge carrier in case of in NPN transistor will be what? It's electron, and that too it will be mostly supplied from emitter. So emitter will supply electrons, and there are only few holes actually here. So some electrons will be absorbed here in base. So you can say some electron will be absorbed this side, they will be transferred this side, and remaining, because like mostly electron will be passing towards collector, and that's why it is termed as collector, because it's collecting whatever number of electrons or charge carrier transferred by or emitted by the emitter. This is how actually a transistor, NPN transistor, symbolically we draw it. There is proper symbol actually. So first thing is electron will be supplied from this side, these electrons will be moving, and few electrons will be combined in the base, remaining will be transferred to collector side. So some electron will be done. So for this you can see the current will be this way, and current will be this way, and some current will be this way, is it? So symbolically we draw it this way also. it's this is also symbol of a transistor. And now which one is base, which one is collector? To identify that, we draw a arrow on emitter, and arrow actually is drawn in the direction of current. So here you can see from emitter current is going outward. So here I can write its current is going outward, then this is your emitter, and because current is going outward, so that's why it will be a NPN transistor. Clear? If I draw outward arrow this side, that means it will be still NPN transistor, but in this situation this will be emitter and another one will be collector. So this is your NPN transistor and this is emitter. Remember that here NPN transistor can also be drawn this way, this, and now if I am drawing here arrow this side, this is also NPN transistor, but in this situation this is emitter. Okay, so that is your NPN transistor. Majority charge carrier is what? Electrons here, that is supplied by. Another possibility can be PNP transistor. So in case of PNP transistor, between two p-type semiconductor, one n-type semiconductor is sandwiched, and that transistor is termed as PNP transistor. So here also this is the situation. This is one n-type semiconductor is sandwiched. Again 3 terminals, and even from thickness you can have idea that this will be like emitter, base and collector. Highly doped, so here the depletion layer thickness will be light, or compared to this depletion layer junction it will be like thin. This is another one. So here it's like P holes will be like highly doping, more number of holes will be here. Ideally it's not that in p-type only holes are there, some electrons are also there, but I am not drawing, just to make things faster, but actually there will be some electrons also, so some electrons will be also there. Similarly here also, but because it's moderately doped, so this is p-type, and there will be electrons here on this, and that too it's lightly doped. And hole will diffuse this side. So here you will have positive on this side and negative charge on this side actually. And similarly here it's positive and negative. So this is, and now see here, whenever some biasing is done, some potential drop is or it's connected in some circuit. So in that situation, what will happen? Majority charge carrier in this situation is holes. So majority charge carriers is holes. Okay, so now holes will flow this side, and again holes, some of the holes will be combined to electrons here in the base and they will be transferred here. So you can say in the direction of movement or motion of holes, we can consider the direction of current. So here current will be toward this side, and it will be like remaining, you can say, few electrons combined here, because the number of electrons available here itself is very less, so all holes cannot combine in the base, so mostly holes will be passing here actually, and they will be passes to collector side, so the current will be passing this side. So in this situation, that is how actually current flow, and like symbolically this is the representation, or that is how we represent a PNP transistor. So its transistor symbol is exactly same, only to differentiate it from NPN transistor, first thing is here current is flowing towards the base, or is it towards the transistor, or is it? So in this situation, and it's again entering in actually emitter, so current direction will be towards the base, and in this situation this is your emitter and this is collector. And there can be another possibility where the emitter is on other side, let's say this. So again P and P, and this is also P and P, so always current will be towards base. Remember that current will be always towards base. P and P, this is also P and P. Only the difference between these two is here this is left side is emitter, here right side is emitter. So that is your NPN and PNP transistor. The mobility of holes is actually less compared to electrons. So the flow, you can say electrons can flow easily. Mobility means that measurement how easily charge carrier can flow, because in this case holes means some like we can consider the complete atom is moving. That means actually like whole movement is considered as whole means like it's atom having some vacancy, is it? So another electron is filling, but still we consider that it's like complete atom is moving. So the but remember that atom actually doesn't move. Just for understanding purpose I was calling it like that. So in case of like holes, it's not easy to move actually, so the mobility is for PNP transistor is less. So preferably we most of the time uses NPN transistor, and in this syllabus we will talk about mainly NPN transistor also. So this is about, so now like here there are three terminals: emitter, base, collector. In normal circuit, whenever we are using, so there are two terminal, some input is given, some output is taken out. But in this situation, how the combination, how the connection can be made? So because there are three terminals, so one of the terminal is kept always common. So either emitter can be like kept common, base can be also kept common, and collector terminal can be made common between input and output. You can connect input between emitter and base and output between collector and base, then your base will be common. So this is your common base NPN transistor. Similarly configuration, similarly you can connect like one common to this emitter. So emitter will be made common, so output will be connected between emitter and collector, and input will be connected between base and like if I'm making this is common, then base and emitter input will be connected this. So input here and output here. So in this situation you can say emitter will be, so there can be three configuration: common base, common emitter, and common collector. All these configuration you can easily check in either book. Okay, so now mainly here I will be discussing things from common emitter configuration. I will try to explain how a transistor actually work, how current flow, how things are controlled here. For the common emitter configuration, the input output characteristics are all same, even functioning is also all same. So if you understand the exactly like characteristic input output for common emitter, exactly same variation will be there for remaining. So let me just first explain you the input output characteristics of NPN common emitter transistor. Okay. Okay, so let's next discuss about input output characteristics of transistor. And before that, I just want to tell you something like about working and like how your charge carrier and current flow. And in this case of transistor, how we like do setup. Another point here is that I'm using only common emitter configuration of transistor. We have three, but because this is, you can say, most widely used, and another reason is this is in our syllabus, mostly problems are asked based on common emitter configuration. Here problems are asked like related how input output current, resistance, voltage, some parameters of it, this and how it work as different devices. We will try to discuss that part only. So now let me start like how it actually works. Transistor based on these two voltages, whether your emitter, collector and base emitter, these two junctions are forward bias, reverse bias. Based on that, transistor actually work in 3 stages, or it's in like 3 states: active state and saturation state and cutoff state. I will tell you the meaning of exactly and in which state what will be the this will be forward bias, reverse bias, in which state what will be the condition of this battery or this junction. So let me just tell you. So now I am talking about active state. So let's say this battery is connected. You can simply understand here, if this battery is not there, then what will happen actually? These electrons will feel some resistance because of this potential difference arising at this point actually. So here these negative polarity will apply some force when these electrons can't jump. Similarly, you can say, so these can't jump this side and they can't go that side also. The current will be 0. Now when we are applying this battery, it will try to push this, and this resistance that these electrons are experiencing because of this potential drop, that will be countered by this BBB battery. So what happened actually, these electrons feel some push and they are pushed towards base side, but base has a limitation that it doesn't have more number of holes. So all the electrons jumping or moving from this side to base here this way, all electrons cannot be combined to holes in the base region. So only few electrons will be combined here, and electron will be moving this side, so some that will constitute some base current. Remember that. And remaining electrons, they will also feel some force or some resistance due to this battery, but they will feel some attraction due to this, and to pull them that side, we are also using another battery towards collector side, and that will help to pull these electrons. So that way the remaining mostly electrons will be passes to collector. So this way actually here we can see, as electrons are moving from emitter towards collector side, only few are combined here with the holes. That is considered very small current in the base, and the remaining electrons are pulled, you can say, by this battery towards the collector, and that will those mostly electrons will move this side. So that will constitute, we call this is collector current, and we call this is base current, and this is termed as emitter current. So IE, the name simple suggests this is called collector current because it's flowing towards collector terminal of the transistor. Similarly, IB is base current, and so on. IE is emitter current. Right? And from here also you can see actually, if I have simply Kirchhoff's current law here at this point, at this junction, in that situation I can write the relation between these 3 currents will be IE is equal to IB plus IC. So you should remember this relation. This is the relation between these 3 currents, right? And there will be some potential drop between base and emitter terminals of this transistor. We are calling that as VBE, and similarly there will be potential difference between collector and emitter junction or terminals, so that we are calling VCE. Here many times we require to apply KVL in these loops actually. So how we can apply KVL? That is also this relation between these, that we are assuming that here we will consider one loop this way, another loop this way, and if the direction you can take any, but means another loop will be this one and one loop will be this one. So KVL we can go in this way, and similarly in this we can go KVL in that direction. So KVL in, let's say, loop 1, this is loop 2, KVL in loop 1. Then from here I can get this is VBB plus, and if there is some resistance is connected, then we will write here actually IB minus IB into RB. And in this situation definitely, because you can say in this complete loop potential drop will be 0, so definitely here it should be minus, we can write DBE, and that will be 0. And similarly here in this you can write KVL in loop 2, and that will be VCC minus VCE equal to 0. So that is a simple relation. Another thing here, we write some parameters for this current, that is alpha and beta parameter, alpha and beta parameters for transistor. So that alpha we define, alpha is the ratio of IC divided by IE. So you can see actually here, as I told, IB will be in microamperes. This is like very small current, and IC will be in some milliampere. Compared to this current, that will be quite large, and the sum of these two will be this. So you can say that alpha will be like this. This is the mostly, you can say almost equal to IE. So alpha is like you can say almost equal to 1, but it's less than 1. Is it? Value of alpha normally. Beta parameter we define, that is IC divided by IB. This is called beta parameter. So here beta value, this is in milli, this is in microampere. So it's around, beta is around 100 or 200, even more than that. So that is another point. In this situation, we are using a DC source. If some AC is also connected, or AC sources, AC power is supplied, in that situation we write alpha beta parameters for AC, that is delta IC by delta IE, and so on. I will write those things later. So this is how actually here current is moving from like you can say charge carriers, that is mainly electron, because emitter is n-type semiconductor. They are moving from emitter towards base, mostly are passing from base towards collector, and that's way. And this is constituting base current, emitter current, and collector current. Base current very small, collector current it's like mostly, or you can say emitter current is mostly passing towards collector. So this is how. Another very important point here is that this current in this transistor is basically controlled by this junction, base emitter junction. So basically, and whenever we are using it as something like in device, we give some input and we give some output. So normally input is given in this side in base emitter junction, and output is taken toward this side. So these parameters, these variations of this with the current is called input characteristics, that my input parameter that I'm going to discuss here. And similarly, this IC versus VCC, we call that output characteristics. Okay, so this is just how like things work. Remember that if we are controlling this, this will control the base current, because you can see if here this junction is in reverse bias. Remember that. This will not allow any current to pass from emitter towards base. So that will also block the current this side almost. So here, that's why here if IB is 0, we can write IC is equal to beta times IB. So if IB is 0, automatically IC will be also 0. So this is just basic things how like here charge carrier electrons are flowing in the transistor. Now this is one circuit diagram for studying the input-output characteristics of common emitter and PN transistor. Another point, as I told, these two parameters are termed as input characteristics, and these two are called output characteristics. We understood this part, that how exactly what is happening. So the inside part, view of this is that actually. Okay. So now what we want to actually here, this is experimental setup in your 12th class. You can do it in your laboratory also. And here what we do is that first we want to study how these two things, like if I'm changing this base emitter voltage, then how this current changes by keeping the value of this VCE constant. Another way is we will study how these two things vary, how these two things relate by keeping this IB base current constant. So these two we are going to see. So here it's sort of like experimental result. I will try to connect that how that experimental result actually work. So let me just erase some part. Okay, so now we are going to see input output characteristic, and here I have this rheostat, one battery is connected here. By moving this rheostat, I can change this like VCE, the potential drop across collector emitter terminal. So we can move this up, down, and let's say we are setting this VC some value, and then here, so we make it constant for one side, and then what we do is actually here by changing this state, this resistance, we can get different values of VBE, and we will start, let's say we are moving it up to here, so here the VBE is initially very small, and then we will try to see how this current ID is varying. So here we can say like initially, let's suppose VCE is some constant value is maintained, okay, this is fixed. Now we see actually, so this is can write the potential drop VBE, and this is delta IV, the current, base current. So here if 0, you can say almost 0, and here 1 volt, then it's like 0 current, still some 2 volts, still some 0 current, some 3 volts, some, then we will get some 1 microampere. This will be automatically in microampere. 3 volts, then you will be getting some like next is 4 volt, then it's 5 volt, then it's 3, and so on, 6 volts, so it's 4. So you can see here actually this is all these values I am taking just random, but the variation I am not saying it could be like exact because that will depend on your setup, but this is one of the probable values. So here as you are increasing this voltage, if this current is increasing, and we plotted actually with a graph of input characteristics, that is this versus delta VBE for some fixed value. So this comes initially, you can say up to some fixed, some certain level of VBE, there is no current in this, and after that the current start increasing like this. It's not exactly linearly, it's something like that. Is it? So this is for some, let's say VCE value 1. Clear? Now let me try to explain you how this is happening actually. So I just told you the diode actually. You can see this transistor is actually what? You can say it's like a 2 diodes. If we are combining 2 diodes, then we are getting this transistor. So this input characteristics means this is base, like base and emitter part. Just forget about this collector part. So here base emitter, this is actually, and what is this? This is just one diode. And when this potential drop is very small, you can see here potential barrier will be like quite high. And when this potential drop is even smaller than this potential barrier, in that situation, this will be in what? Reverse biased. And you can see up to the point where this is not countering this reverse bias or the barrier, is it? Up to that point there will be no current. So this is 0 current up to, you can say, this barrier, potential barrier. After that, you can see this is in forward bias. As you increase this potential difference, the current will start increasing, and that is what exactly we are getting. So it's just like one diode, and which is in forward bias. So this, you can see this graph also matches with the characteristic curve of forward bias, characteristic curve of diode. So exactly that is. Now next point is that now I am increasing this VCE, and how this VCE will affect this graph or this variation. So now what is happening here actually, see, if I am initially maintaining VCE some little less value, is it? You can say this is what actually like for this barrier, this positive, is it? So here you can just look at it, this just one second. Okay, so here next, if I'm increasing this value VCE, is it? Then what happening actually, this try to understand, this is the barrier potential, and you can see this battery is sort of in support of this potential barrier. So it will try to, if I just look at this terminal, this battery is trying to support this barrier, so it will increase the barrier further. So now next, you need to increase this battery to bring this base emitter junction in forward bias, and then it will be just like normal variation. So because of that support of this potential of this battery at this junction, you can say the graph will shift towards right. It will start, the current will start even at higher potential, and then it will be just like normal way. So this is, and similarly if you are increasing further, it will be something like this. So this is VCE, this is VCE, that's a 2, and VCE 3. So that is how your input characteristic curve or input characteristics varies. This is your input characteristic curve for A and PN common emitter transistor. This variation, this graph is exactly same for common emitter, common base, and common collector, right? But here I am drawing it only for common emitter. So I hope you understood why every point, why this is things are working, and how we are able to correlate. So this VCE here, if I just tell you, this is greater than VCE 2, greater than VCE 1. Right? This is about input characteristic of transistor. Similarly, right? And then, one thing is, you can see, yes, it's just like playing some role, but mainly complete role is played by this potential drop. Is it? If this is small, this is like very less, such that it's even smaller than this barrier, no current is flowing. Once it is countering that barrier, then it's like forward bias. It's just like simple diode in forward bias. Okay, let's talk about next is output characteristic. Okay, so output characteristic of a transistor means variation of this current with this voltage. For that, now we will keep this value constant for one situation. We are keeping this constant, and then we will try to vary this voltage, and we will observe how this current is we are getting. Okay, so now in this situation, you can say like these two will be like mainly playing some role, but yes, this is controlling it, right? Okay. Another point here is this, you can see this battery, it's mainly controlled by this junction, you can understand it this way. And what is this? This is in reverse bias connected. So here, just for rough idea, because this was in forward bias, so the characteristic curve mainly depending on this junction, and it matches with the forward bias diode. So exactly you can get some idea, and we get it even practically true, that this characteristics will be something similar to reverse biased diode. And when we are actually plotting this variation of delta ICE versus IC versus VCE for some fixed value of base current, what happened? It initially just like here I'm drawing this graph in first quadrant. This nature will be just like this. Is it? So here what happened, up to some certain value, this increases and becomes a constant. I just one second. Okay, so about output characteristic, if we just look at the result from the experiment, it looks like this actually. This variation is almost linear up to some certain point, and after that it becomes constant. And so this is for one IB value, you can write delta IB 1. Similarly, if we are increasing this current, right, then this delta IC increases with respect to this up to some certain level, and then again it becomes constant. So if the graph looks like this actually, this way, and similarly it increases further, and then again it becomes constant, and so on. So this is delta IB 2, delta IB 3, delta IB 4. Variation of output current with this VCE voltage for different value of this base current. Now let's try to understand why and how this is happening this way actually. First thing is, as I told, in a transistor things are actually controlled by this input characteristics. So here, this what is happening here, this is controlling it. So when this is low, when no current is flowing through this is in like you can say reverse bias, then nothing can't happen actually here, because this is even supporting this reverse bias, so no current will be there, so IB will be 0 and IC will be 0. But if we are increasing this, then definitely more number of electrons will be passing towards base side. Only the point is that more number of electrons are passing. Try to understand it. From here, let's say I will say some 10 electrons are passing, and here 2 electrons are combining towards base side, and then 8 are passing towards this side. Now, if I am decreasing it, what will happen actually? Sort of you can say it will try to pull less number of electrons. Understanding? So when the potential, this VCE, delta VCE, potential difference across collector emitter junction is low, you can say less number of electrons will move this side. You can say it will prefer to move base side. Understanding? More electron will be moved this side. But so when we are increasing this, there will be, you can say, the competition between this and that. So if you are increasing VCE, basically here this voltage, then more number of electrons will pass towards the collector side. So that is what exactly happening. Initially there is competition between this and that. So as you are increasing this, then more current will be passing towards collector side, and that is how this is varying actually. Understanding? So that is this initial varying set. Now as we are maintaining this, is it? So then up to that, like this we are making it constant, means IB is constant. Then after that, like you can say there will be some maximum number of electrons, because the number of electrons passing from here is mainly controlled by input side. So when we are making this constant, means the number of electrons, let's say I am saying 10 electrons are passing from emitter side, then that is constant. You can't make it like more 15 by increasing potential drop across collector emitter. So that is why this is made constant. Only the point is that after certain time, as this is increased, you can say mostly whatever the number of electrons can pass towards the collector, all are passing. Then as you increase further, there is no effect coming on this collector current, so this become constant. Next time, as you are increasing this base current, that you will increase by increasing this. So you can say more number of electrons. Now instead of 10, now 20 electrons will be passing. But still there will be competition between this and this current. So you can say initially, as you are increasing this, more number of electrons will be passing this side, and here also like as we have already increased base current, so this will be also increased. So the variation will be again a little bit straight line between this and that graph. After certain instant of time, certain voltage, this, you can say the maximum number of electrons which can pass from here towards collector is passing. Then as you increase this VCE, this voltage, no further electrons can move. Means the number of electrons moving this side cannot be increased by increasing this. So again, after that time, your delta IB increases, delta IC also increases. It comes in some milliampere, let's say 1 milliampere, or I will write it some 10 milliampere, this is some 20 milliampere, this is some 30 milliampere, and this is some 40 milliampere. This is in microampere, so some 10 microampere, 20, 30, and so on, microampere. These values I am just writing randomly. Practical values will be different. Okay, so that this is this graph, variation of output current means variation of this current, collector current, with this voltage is termed as output characteristic of, or output characteristics of transistor, and variation of delta IB with delta VBE is termed as input characteristics of transistor. Remember that in a transistor, things are controlled by input parameter, even output things are actually. Yes, the variation is, but overall here, as we told, the relation beta times IB is equal to IC. So if IB is 0, automatically your IC will be 0 also. So means this current is also controlled by this side actually. Yes, we are increasing this voltage, variation is this. This is about input characteristics. Remember these relations, remember these variations. Here, these all things are varying with increasing, like changing this. Normally, this is actually active region of transistor, this is like up to this variation. This is in saturation region, saturation mode of transistor, and when you can write IB is very small, IC will be also 0. So when both currents are 0, that can happen when this is reverse bias, this is also reverse bias, then your transistor will be in cutoff region. Okay, so this is about the characteristics of transistor. Let me write a few more things, then we will move on how we can use this transistor for different applications. So I hope you are clear with this variation. Remember, it is important actually. So these are variation of delta IB versus VCE. So this is the curve, and definitely delta VBE divided by delta IB will give you what? This term is called input resistance. Input resistance. And that is given by R input, and that is equal to delta VBE divided by delta IB for some fixed value of delta VCE. And here you can see it will not be constant, it will be changing. So this will be a dynamic resistance. And we call this is input resistance. Similarly, this is your output resistance, and here, so the slope might not exactly so, because this is the current and this is the voltage. For this reason, actually I can define the output resistance. This is given by R output is equal to delta VCE divided by delta IC for a fixed value of base current. So this is termed as output resistance. And as I told, alpha beta parameters for DC, I told alpha is what? IC divided by IE. Beta parameter is IC divided by IB. For AC, you can write alternating current. We write alpha parameter is delta, because here there will be variation, change we measure actually in case of AC. So delta IC divided by delta IE, and beta parameter is delta IC divided by delta IB. Actually, if we look at it, then these two parameters values for AC and DC, it's almost same. So we take it actually same value, equal value. Alpha and beta parameter values are same for both AC and DC supply or DC current. So these are some like terms, some points about transistor. There is one more term actually sometimes that is asked, that is called transconductance of transistor. Sometimes this term will be asked to you, what is the transconductance? So what is that? We denote it G and term. G is basically conductance is inverse of resistance, and for conductance we use the term, we use the letter or like G actually. So here we write G amp, and that is equal to, you can write one inverse of resistance, but it's not simple conductance. Here it's delta IC divided by just yes, so this is delta IC divided by delta VBE. It's actually the output current variation with input potential drop. So this term, this ratio is simply termed as transconductance of transistor. So this is all about little how transistor work and its input and output characteristics. Let me discuss in the next class, next lecture, how we can use transistor as amplifier, transistor as switch, and transistor as oscillator also. So thank you so much.